Okay, so here's in front of us we have a magnetron tube that's been cut apart into the basic elements. Over here we have the stem end. This has the filament connectors and the high voltage insulators, or bushings as they're sometimes called. And inside, this is part of the inside of the tube. This is the filament itself, and this is part when the tube is operating gets white hot. It's actually heated to about 2100 degrees centigrade, and this is the source of the electron emission that allows the tube to draw current and function. In here, this is the anode, and in magnetrons, the anode takes the form of several spokes, or vanes as we call them, that are around and form a circle. And at the center here, the tip of the vane is a ring comes to a diameter. That's particular diameter to helps determine the frequency of the tube. And the inside the tube, each of these vanes is a certain length, and the space between them and the amount of surface area that's near each other forms a tank circuit, with a capacitor being made out of the faces of the vane tips, and the length and width of the vanes creates an inductance. That capacitance and inductance causes a resonant circuit, and it's all set up to operate at 915 megahertz, which is the frequency that we want for our food processing machinery. And you'll see inside here there's a couple of little rings that go in this around the outside of the anode surface, and there's two on the other side as well. And these rings, we call them mode locking straps, and they help make sure that the tube runs at 915 megahertz without shifting to some other frequency, which we don't want. And when the tube changes frequency, we call that moding, and that can cause damage in the tube. These rings, or mode locking straps, are connected to alternate vane tips. So this outer ring is connected to 5, and the inner ring is connected to the other 5. And the same on this side. It's exactly the same on both sides. So when the tube is running in the correct mode, or what we call the pi mode, at 915 megahertz, the two vane tips that are connected, and each of the alternate vane tips that are connected to one ring, are all at the same voltage potential, so there's no current flow in the ring. And when the tube switches to a different mode, the vane tips are no longer actually in the same phase or polarity, and so they're not at the same exact voltage potential any longer. That induces current in the strap, and in most cases the current is severe enough to actually melt the strap, and it damages the tube. So the tube doesn't function any longer, or at least not very well. Sometimes they'll still function, but not reliably. So that's kind of how the basic oscillator circuit is set up. And the way that the oscillation is kind of started, when the electrons from the filament are coming off, the anode is at a much higher voltage, and it attracts the electrons towards the anode. And then surrounding the magnetron tube is a large electromagnet, or solenoid, and the magnetic field is created on a vertical axis. In other words, it's in line with the tube, which is perpendicular to the direction of the electron stream that would normally flow without the magnetic field in place. So when the magnetic field is at the right strength, it interferes with the electron stream, and they start to go in a kind of a curved path, and some of them are reflected back into the filament, some of them actually make it to the anode, and it causes an oscillation to occur, which excites the resonant circuit, and then that starts the oscillation at the 915 megahertz, and it's stable, and it runs continuously as long as we maintain the magnetic field in the right strength, and the filament temperature is the correct temperature to give us adequate electron flow. So this part here, this is one of the pull pieces. This is an iron part. It's been copper plated, and then this end, the other pull pieces here, got a steel ring on it. These make up the magnetic circuit, or part of the magnetic circuit, and they focus the magnetic field to stay concentric and in straight lines on axis with the center line of the tube. So these couple with the external pull pieces, which are part of the solenoid assembly. One goes down at the bottom under the dome, and the other one goes on the outside, and that's what holds it into the solenoid. And so that's the magnetic circuit. So to get the power out of the tube, there's three little posts or standoffs here that are attached to three of the vanes, and then we have an antenna or a probe piece that attaches to it like this, and these pick off the signal from because the current that's in the veins, that's flowing in the veins, creates a voltage potential. So we pick it off in a little bit in the middle, sort of like a middle tap on a transformer, and it induces a voltage field onto the probe. And the probe is, the whole tube is covered by the dome or an RF window, and this is part of the seal, the vacuum seal. And this whole assembly, when it's put together, is down inside the waveguide, what we call the transition, and that radiates the RF power into the waveguide, which takes the, conducts the RF power down the waveguide to the load, into the oven cavity. And this tube is water cooled. There's cooling ports here, which the pipes have been cut off for display, but as you know, the water is flowing through the tube. And these, each of these vanes is actually hollow. There's a series of water passages into the vane, and they get pretty close to the tips. They're kind of under where the straps are. You can't really see it, it's all fully welded together, but there's water passages in there, and we bring the cooling water very close to the tip of the vane to get the heat out before, otherwise the copper would get hot enough to vaporize and damage the tube. So it's important to have cooling flow all the time. Even when just the filament's lit, there's enough heat in the tube, it could injure the tube unless there's cooling water flowing. So now the tube, to operate successfully, has to have anode voltage, and it has to have the filament supply voltage, and it has to have the magnet, and this is the schematic for that, and I'll explain that shortly.